Related rates, another wonderful set of word problems. To do a related rate problem, as with all problems, you need to understand the problem. Drawing a picture frequently helps. Introduce notation to your picture, labeling what's going this way and what's going that way to get a clear picture of what's going on. You want to write down what you know and what you are looking for. You want to write out the relationships between the variables. Then take the derivative with respect to time. Fill in what you know, solve for what you want. Do not plug anything that is changing until after you take the derivative with respect to time. Now, if you have a ladder that's length 12 and that's not going to change, fill that in. But if you have a car that's driving down the street and you know we're asking something when it's 5 miles from your house, do not fill that in because that's going to change. First example, air is being pumped into a spherical balloon so that its volume is increasing at a rate of 11 cubic centimeters per second. How fast is the radius of the balloon increasing when the radius is 50 centimeters? So cute as that picture is, it doesn't help me see what's going on. So here's a nice sphere with a radius. So what are we given? We know change in volume with respect to time. So the rate that the volume is increasing is 100 centimeters cubed per second. The time we care about is when the radius is equal to 50. And we're looking for the change in radius. So I need an equation that relates volume to radius. And the volume of a sphere, as we all know, or we will figure it out if we ask ChatGPT, is 4/3 pi r cubed. So I have my equation. I take the derivative with respect to time. We get dv dt is equal to 4 pi r squared dr dt. Remember, like when we did this with implicit differentiation, when we took the derivative with respect to x, we just left it as 1. But now we're taking the derivative with different variables, all of them with respect to t, so we have to always remember to have that dr dt, dv dt, whatever variable we are taking the derivative of. When we do the chain rule, we need to include the d whatever dt. Okay, so we have dv dt equals 4 pi r squared dr dt. I'm given dv dt, I'm giving r squared, and I'm looking for dr dt. So let's fill in what I know. So I have 100 equals 4 pi 50 squared dr dt. Solving for dr dt, I get 100 over 4 pi 50 squared, which is approximately equal to 0.0031831 centimeters per second. So that is how fast the radius is increasing when the radius is 50 centimeters. Next one, another standard favorite of this section. We have a ladder, 100 feet long. It's resting against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So first, picture. We have labels. We're going to call this x, and we know the bottom of the ladder is going to the right away from the wall. The other thing I'm going to label is y. The distance from the top of the ladder to the ground is y, and it's getting smaller. So what do we know? I know the ladder is 10 feet long. I'm given that dx dt is 1. I'm curious about what's happening when x equals 6. I'm looking for dy dt. What relates all these things? Well, I know x squared plus y squared equals 10. So let's take the derivative with respect to time. I have 2x dx dt, 2y dy dt equals 0 because the ladder is not changing. I'm going to divide by 2 to make my life easier. And then let's plug in what oh, wait a minute. I know x, I know dx dt. I know I'm looking for dy dt, but I don't know what y is. So I need to go off to the side and figure that out. At the time I care about, x is 6, so I have 6 squared plus y squared equals 10 squared, which means y is equal to 8. Okay, let's try this again. I have 6 times 1 plus 8 times dy dt equals 8, which means dy dt is negative 6/8 or negative 3/4 foot per second. Makes sense it's negative because my y is getting smaller. A water tank has the shape of an inverted circular cone with a base radius of 2 meters and a height of 4 meters. If the water is being pumped into the tank at a rate of 2 meters cubed per minute, how fast is the water level rising when the water is 3 meters deep? Why would you have an inverted circular cone? It's just so you can do calculus word problems. Anyway, let's draw a picture. So I have my conical water tank. The height is 4, the radius is 2. The water level is at h, and the radius at that point is r. The r and the h are changing. I'm given that dv dt is 2. It's positive because it's filling up. I'm looking for dh dt when h is equal to 3. I need something to relate these two. I know volume is 1/3 pi r squared h, but I only want one variable. So I need to figure out a way of getting rid of the r. Going back to the cone, look at what I've highlighted. This is a triangle, and this is a smaller triangle, and the two triangles are similar, so I can use similar triangles. I know that 2 is to 4 as little r is to little h, which means r is equal to 1/2 h. Let's plug that back into the volume equation and simplify. Now I can take the derivative with respect to t. I get dv dt is equal to pi over 4 h squared dh dt. I'm going to fill in what I know. So I know that dv dt is 2. Time I care about, h is equal to 3. Then I'm going to solve for dh dt and get 8 over 9 pi, which is approximately 0.282942 meters per minute. Next example. Fred's car is traveling east at 50 miles per hour. Ethel's car is traveling north at 60 miles per hour. Both are headed for the intersection of two roads. At what rate are the two cars approaching each other when Fred's car is 0.3 miles from the intersection and Ethel's car is 0.4 miles from the intersection? So let's draw a picture. Yay, there's my cute picture. They have the same cars. Fred's car is heading to the east. Ethel's car is heading north. Let's label this distance F for Fred and this distance E for Ethel. This is the distance we care about. I could label it D for distance, but I hate saying dd dt. It's just too many D's, so I'm going to call it S. I'm given that df dt is negative 50, negative because F is getting smaller. I know F is 0.3 at the time I care about. dE dt is negative 60, and E is 0.4 at the time I care about. I need to figure out what ds dt is. The relationship between the three variables is f squared plus e squared equals s squared. I'm thinking I'm probably going to need to figure out what s is at the time this all happens, so I'm going to go off to the side and do that. I know that f squared plus e squared equals s squared, so s is equal to 0.5. Nice Pythagorean triple there. So let's go back to f squared plus e squared equals s squared. I take the derivative with respect to time, so I get 2f df dt plus 2e de dt equals 2s ds dt. Dividing by 2 because I like to do that just to clean it up. Now I'm going to plug in what I know. I know lots. So plug in the 0.3 and the negative 50, the 0.4 and the negative 60, and the 0.5. I need to solve for ds dt. Simple linear equation. I get ds dt is negative 78. So the distance is decreasing by 78 miles per hour. Last example. A man walks across the stage at a speed of 4 feet per second. A spotlight is located 20 feet above the stage and is focused on the man. At what rate is the spotlight rotating when the man is 15 feet from the spot directly below the spotlight? So first we need a picture. There we go. We've got 20 feet for the spotlight. It's up here. I didn't draw it. Have a man here. I need to label the distance from the man to directly below the spotlight. Let's call it x. So I know that dx dt is negative 4 because he's getting closer to the spot. And I care about the time when x equals 15. They're asking about rotation, so I need to label that angle. Let's call it theta. So I am looking for d theta dt. What relates these things? Well, I know that tan of theta is x over 20. Taking the derivative, I get secant squared theta d theta dt equals 1/20th dx dt. Now I could figure out what theta is at this time, or I could use the Pythagorean theorem and just figure out what the hypotenuse is and then read it off the triangle. And that's what I'm going to do. I'm going to label the hypotenuse h, how original of me. I know that x squared plus 20 squared equals h squared. Fill in what I know. So I've got 15 squared plus 20 squared equals h squared. So h is equal to 25. Now if I read the triangle, the secant is 1 over cosine. Cosine would be 20 over 25, but this is secant, so I have 25 over 20. It's squared times d theta dt, and then 1/20th times negative 4. Simplifying this, I get d theta dt equals negative 0.128. Now what the hell does that mean? Okay, we did this in real numbers, so that means radians. Theta is changing at a rate of negative 0.128 radians per, what's our time? Per second. That doesn't help me with revolutions. And I don't have a really good picture of that. The negative just means we're going clockwise rather than counterclockwise. So let's figure out what that is in terms of revolutions. Well, there are 2 pi radians in a revolution. So if I divide this by 2 pi, I get negative 0.02037 revolutions per second. Not enough to wrap my head around. Let's try how much it would be per minute. So I multiply by 60. That makes more sense to me. I have negative 1.22 revolutions per minute. Negative just means going clockwise, and about 1 1/4 revolutions every minute. So that's how fast the spotlight is rotating when the man is 15 feet from directly below the spotlight. When you are doing related rates, you want to write down what you know and write down what you're looking for. You want to find an equation that relates those variables. Once you do that, take the derivative with respect to time, fill in what you know, solve for what you need. Just take it nice and easy. Don't try to magically figure out the answer in one step. Just take it little chunk at a time.